Now, using StatCrunch, we would enter the observed frequencies in one column and the corresponding expected proportions in another column. So StatCrunch wants the expected proportions, not the expected frequencies. So the two lists in the calculator are observed frequencies and expected frequencies. The two columns in StatCrunch are observed frequencies and expected proportions. Okay, when we actually run the chi-square goodness of fit test, the StatCrunch will actually compute those expected frequencies for us. Then we would choose stat goodness of fit chi-square test. We'd pick those lists, hit compute, and on the output screen we would see a chi-square value and a p-value. So either way either technology we use, it's going to use the same formula for the chi-square test statistic, which means we have the distribution of chi-square, which is this right skewed distribution starting at 0 and running off over here to infinity. And our p-value is always going to be the area in the right tail, where again the test statistic that we see on the output screen is this number that is the cut score between the unshaded and the shaded region in our distribution. And then our decision and conclusion exactly the same as they've been through all of hypothesis testing. So example 11.2.1, chi-square goodness of fit test. So suppose you have a die and you're curious if it's fair or not. If it's fair, then the proportion for each value should be the same. You need to find the observed frequencies, and to accomplish that you roll the die 500 times, and then you count how often each side comes up. So the data are in table 11.2.1. So we want to know if the data show that the die is unfair, and we want to test that at the 5% level of significance. So in our table here we've got they observed 78 ones, 87 twos, 87 threes, 76 fours, 85 fives, and 87 sixes when they rolled the die for a total of 500. And as we look at those, they're all fairly close to each other. They didn't all come out exactly the same. But with 500 die rolls they can't, as we'll see here in a second. But if the die is fair, then the probability of each side of the die is 1/6. There's 6 sides and each should have the same chance of happening, so they each have 1/6 of a chance of being rolled. So to get the expected frequency, we're going to take the sample size, which in this case is 500, times 1/6. So that's why we have in each one of these cells 500 divided by 6. Okay, those would be our expected frequencies in each of those cases. All right, so again, following through phantoms, we don't have a parameter in this case, so we don't have p, which means in the hypothesis test we also don't have a parameter. These are just going to be wordy hypothesis tests for these qualitative tests. So the observed frequencies here we're going to say are consistent with the distribution of a fair die. Okay, so die is fair. And the alternative is going to say that the observed frequencies are not consistent with the distribution of a fair die. So the die is not fair. So again, our next step here is to check the assumptions. Okay, so a random sample is taken. In this case, because we can throw, each time you throw the die, it's a random event. So again, it's whether we roll it 10 times or 500 times, 1,000 times, any of those can be seen as a random sample. Okay, as long as you're not like some little kid who's like trying to roll a 6, and so like trying not to not giving it a good shake before you roll it and trying to actually control what's rolled. But otherwise we're going to assume that they didn't do that and that it's a random sample of die rolls here. Again, the expected frequencies for each cell needs to be greater than or equal to 5, and again, these are the expected frequencies, not what we actually observed. Okay, so the expected frequency for each cell in this case, since we expected the same in each one for a fair die, was 500 times a 6, which if we compute, that's about 83.33. Okay, and that is definitely greater than or equal to 5. Again, no cap n is given, so well, in this case, okay, there's not a finite number of times a die can be rolled even. So in this case, our population size can be seen as infinity, which is definitely going to be larger than 20 times the 500 die rolls that we looked at. Okay. So a little bit different than when we're picking, objects from a population like cars or people or whatever. There's only so many of those, but a die can be rolled infinitely many times. It's not like a die can only be rolled a couple thousand times and then it like disappears or something. So again, the die roll is a little bit different than some of the other data that we've looked at. So if we're going to name the procedure used, in this case the assumptions for the chi-square goodness of fit have been met. All right, so now finding the test statistics. So using the calculator, again, we would go into L1, and in L1 we put all of our observed frequencies. And in L2 we're going to put what we expected if HO is true. And HO says we have a fair die, and if it's fair, we would expect each one of these to be 506. So again, on the output, the screen here, it looks like 83.33 has been entered for all of these, but it's not. In each case, I entered 500 divided by 6, and so if we would actually highlight one of these cells, we would see down below that it is keeping a bunch more 3s after the 83.33 that we see on the view screen here. Okay, so make sure that you're entering the exact expected frequency of 500 divided by 6 and not rounding those values too soon.